These are the summary notes for section 1.5 in Unit 1, Fluids. And our topic today is Archimedes' principle. Archimedes' principle states that the buoyant force on an object is equal to the volume of the water displaced. Or I should say fluid, because it might be a fluid other than water, like oil or alcohol. Now, if the object is completely submerged, then the volume of the fluid displaced is the same as the volume of the object, because the object is completely underwater. So if I just make a quick sketch of a vessel of water, and there's a cube in the water here, the entire object is under the fluid, so the displaced fluid is equal to the volume of the object. For an object that is floating, then it's a little bit different, because the object is actually sticking out of the water, and only the volume of the object under the water is equal to the volume of the fluid displaced. So let's do an example with a floating object. Let's take a look at an ice cube. So in our example, we'll have an ice cube floating in a glass of water. Now, ice is really unusual. It's one of the only substances that when it turns from liquid to solid, its density actually goes down. So the density of ice is 917 kilograms per meter cubed, and the density of pure water is 1,000. Oops. So let's say that we have an ice cube that measures 2 centimeters on a side. Let's figure some things out here. Here's what we can figure out so far. Number one, what's the mass of this ice cube? Well, we can figure that out, right? We've got the dimensions and we've got the density. So the volume of the ice cube, the volume of a cube is the side cubed, so that'd be 0.02, oops, not centimeters, meters cubed. So I converted this to meters. So that is 8 times 10 to the negative 6th square meters. Okay, and then the mass is going to be the density times the volume, which is 917 kilograms per meter cubed, times 8 times 10 to the negative 6th meters cubed. Oops, this is supposed to be a cubed, which gives us 7.336 times 10 to the negative 3rd kilograms. Okay, next, let's figure out the weight of the ice cube. So remember that weight, which the College Board likes to use W. In most of in the textbooks I've used in the past, it says FG. So you'll see those interchangeably. But regardless, weight is mass times the acceleration of gravity, which is 9.81. So we have the mass from before. It's 7.336 times 10 to the negative 3rd kilograms times 9.81 meters per second squared. And when we multiply that out, we get 0.0720 newtons. Okay. Next, how much water is displaced by the ice cube? So this is where we would use Archimedes' principle. This object is floating. For a floating object, the weight of the water displaced is going to equal the weight of the cube. If I were to draw a force diagram for this ice cube, the buoyant force would be equal to the weight of the cube. These things are equal and opposite. And the buoyant force is equal to the weight of the water displaced. So the answer to part C is the same as part B. It's 0.0720 newtons. Oh my goodness. There we go. Okay, next up. Now here's the real trick. How much volume of water is displaced? Well, I know the weight of the water displaced. I know that the weight is 0.0720 newtons. And I would be able to convert that back into mass. If I take 0.0720 newtons and divide by 9.81, I will get back to 7.336 times 10 to the negative 6 kilograms. And then to find the volume, I'm going to take the mass divided by the density. So that would be 7.336 times 10 to the negative 6 kilograms divided by the density of water, which is 1,000 kilograms per meter cubed. And that is going to give me, this was times 10 to the negative third. I got it a little ahead of myself here. So this is 7.336 times 10 to the negative 6th meters cubed. So this is what's really cool about water is that the, oh my gosh, I made another little mistake. I apologize. This is supposed to be times 10 to the negative third. The density, since the density is always a multiple of 1, these numbers match up. Okay. Let's see what's next on our agenda here. Oopsie. Okay, so now we're going to try to figure out what volume of the ice cube will stick out of the water. So it's important to know, we've got the volume of the water displaced. This is the volume underwater. And we know the volume of the cube. We calculated that up here, 8 times 10 to the negative 6th. So the volume of the cube minus the volume that's underwater is the amount that will stick out of the water. So if I take 8 times 10 to the negative 6th and subtract 7.336 times 10 to the negative 6th, that gives me 6.64 times 10 to the negative 7th meters cubed. So if I were just going to try to sketch that, there's the cube. There's my water line, just to kind of give me an idea. And I just determined how much is sticking out above the water. Finally, what we can do is we can figure out the height above the water. Let's figure out how high does the cube project. Above the water line. So to determine that, I've got the volume. Okay, I've got this volume of this box, basically, that's sticking up above the water. And what I want us to remember is something from geometry. I've got a cross-sectional area here. I've got the area of the base. And if I take the area of the base times the height, this little height is how far the cube projects above the water line. And the cross-sectional area I can figure out because I know that the cube is 0.2 or is 2 centimeters or 0.02 meters on a side. And I know that the volume is that cross-sectional area times h. So if I take 6.64 times 10 to the negative 7th, that's my volume, equals my area, 0.004, times height. I can solve for height by dividing. And when I solve for height, I get that the height that sticks up is 0.166 meters. Okay, so that's kind of, that's an example. Okay, so let's try to summarize something important to know for floating objects. So here I've got the situation for where an object is floating in water. And basically what I know is I know that the gravitational force, or the weight of the object, is equal to the buoyant force on the object. And I'm going to make some substitutions here. I know that the weight of the object is equal to the mass of the object. I'm going to write object because I'm dealing with an object and I'm dealing with a fluid. Object and fluid. And I want to keep those straight. So Fg is the mass of the object times g. The buoyant force is equal to the weight of the water displaced, or the fluid displaced, but the fluid displaced is equal to the volume of the fluid times the volume of the fluid, and the volume of the fluid that is displaced is the same as the volume of the object that is underwater. Again, this object, the portion of the object that is underwater is pushing this water out of the way and creating that buoyant force. So I'm going to call this underwater times g. Now I can set these two things equal to each other. So I can say that Fg is the mass of the object, I'm just going to use an O, times g. And the buoyant force, again, is equal to the density of the fluid times the volume of the object underwater times g. Okay, now right off the bat, I see that g cancels out, so that's kind of handy. Now on the left side, I'm going to make another substitution because I know the density of an object is the mass of the object over the volume of the object. So mass is equal to the density of an object times the volume of an object, and I'm going to make that substitution. So I'm going to write the density of an object times the volume of the object equals the density of the fluid times the volume of how much of the object is underwater. And this allows me to make I'm going to turn this into a ratio. So I'm going to divide both sides by the volume of the object. And I'm also going to divide both sides by the density of the fluid. And I'm going to get a really, really handy formula. So here it is. The volume of the object that's underwater, the amount that's underwater, divided by the volume of the whole object equals the density of the object over the density of the fluid. This formula is super, super, super handy. And I'll just do a quick example to show you why. Let's say that I've got, oops, wow, I don't even know what I did there. Nope. Okay, and I'm back. Let's say that I've got a vessel of water, and let's say it is water. Water's really handy because again, that density of the fluid, density for water is 1 gram per centimeter cubed, or 1,000 kilograms per meter cubed. And let's say that I have an object floating in the water. I'll do a different color. So we'll make it kind of a cubic object. And let's say that 1/8, let's say 7/8 of the object is underwater and 1/8 is above. Basically, that ratio then tells me the density of the object itself, because if this ratio is 7/8 and the density of the fluid, if it's water that I'm using, is 1,000, then I can cross multiply to find the density of this object. So I would say that the density of the object would be 7 times 1,000 divided by 8, which is, oh my gosh, my brain has left me. I'll get out my trusty calculator. I guess it was a long summer, everybody. Maybe you have the answer already. 0.875. There we go. So 87.5% is underwater. That means that the density of this thing would be 875 kilograms per meter cubed, or 0.875 grams per centimeter cubed. So again, this kind of ratio is really, really helpful.